Hello, class. I hope that I'm recording correctly and everything. Let's see. Yes, I seem to be coming through. Today, I want to really start into the course material on solid state. And I thought about handling this several different ways. First going into really what an electron is and the material science aspects to that. Of course, what we want to do is we want to probably handle that a little more deeply than you would even in a material science course. And so what I want to do, and I just realized that I don't have my my timer on, so just a second. Okay, I should be back and recording. I have made quite a few of these lectures for various different classes, so this shouldn't be too bad. I'm just going to remove that so that it's set. Okay. Oh, now it's not quite correct. Just a second. Yeah, I should have left that thing up there. There we go. I'll put that back there. That's better. All right. So what I wanted to start on today was to really look at crystals. Let's see if that's on. Yep. I want to look at crystals. I've got two lines up here today, and I wanted to look at the unit cell. I want to look at the lattice structures. And when I say the lattice structures, I mean the Bravais lattice structures of the various different types of packing arrangements that we can have in crystal lattice structures. And of course, when I say crystals, there's a lot of things that are crystalline. Salt, sodium chloride is a crystalline solid that isn't a metal. But for instance, aluminum is a face-centered cubic structure. Iron, or steel as we know it, but it's predominantly steel, is predominantly iron, is a body-centered cubic structure at room temperature, but is a face-centered cubic structure above a certain temperature. I'm trying to think what it is, like 786 degrees Fahrenheit, something. Anyway, I'll get to that later. I'm getting a little ahead of myself here in the crystals lecture. But what we want to do is we want to look at things that are crystalline. Of course, most metals, many conductors. Copper, for instance, is a face-centered cubic structure. Gold, a lot of these things that are very good conductors are different types of Bravais lattice structures. And so that's what I want to get into today, is to look at different crystal structures and crystalline structures, perhaps not as deep as your textbook will get in the third chapter, but we've got to start someplace. And the one place that I think that we all can easily wade into understanding solid state devices and solid state physics is to understand how these crystal structures are put together. And of course, silicon is a crystalline structure as well. So we'll get to that in a little while, but and then of course, how do the electrons work in these crystalline structures? And that's what we want to do later. But the first thing that we want to look at is we want to look at the crystals themselves, right? So when you're looking at a crystalline phase, let's I want to take one that's, let's look at our Bravais lattice structures. And if you'll notice in the reading that you've done, right? If you've noticed in the reading that you've done in chapter 3, you'll see that those 14 different Bravais lattices really are the exclusive total of the different types of crystalline packing structures that we can have. Some of them have higher packing factors than others, and I'm going to look at that today. Packing factors. I know that I decided to keep those to a later lecture, I think, but I think that I might even get into those today because I think it really shows something about how we can determine what the packing factor is for a whole variety of different lattice structures. And of course, different materials have different lattices. For instance, methane is a face-centered cubic lattice. So let's get into the various different types of crystal systems that we can have. And they fall into a variety of different shapes. When we look at the Bravais, I think I'm pronouncing that right. I think it's French. The Bravais lattice structures, there's actually 14 different ones. And what I want to start off with are the ones that we're going to be looking at in the beginning. One would just be, I'm just going to, these are cubic structures that I'm looking at first. And a cubic structure then, a unit cell of that crystal lattice structure would be, in a simple cubic, it would look like that. If I was to draw the back of it, I think you can see that in this cube, and I could just drop down some lines here to, you know, show the invisible backside of that cube, but of course it would have, right at that joint right there would be another atom. So no matter how we look at the cube, we're going to have an atom in each of the vertices of the cube. I should make that a little better. There you go. So that would be a simple cubic structure, right? Now, let's expand and sort of look at this simple cubic structure and see if we could figure out what its packing factor would be. Now, the packing factor is how much of this is taken up by the atom and how much of this, let's say that the atoms are individually touching wherever they can touch, and how much of this is taken up by just air, right? Okay, well, if we were to look at it and draw it, let's say a little better than we drew it there, we would see that one of the faces, if I was to actually draw it so that there was an atom in each corner and each of those atoms were touching, we would see that each of the atoms, right, let's just draw the whole cube here, or at least the part of the cube that we've got, we would see that each of these atoms, right, is taking up, touching each other. So I would draw it like that. And I think you can see that each one of those atoms then inside, I mean, I've got that, and we could see that this atom would be going down back over there, and that this other atom would be going off over to that side. But you can see that each one of these atoms right here, right, is going to be 1/2 of the distance here. So this distance, let's call this A. And in fact, your book, as well as really any book that's dealing with Miller indices or with crystal lattice structures, Bravais lattice structures, is going to name that A. Now, let's talk about A in terms of R. That's supposed to be an R. There you go. So what would A be in terms of R? And we could say that A then is equal to 2R, right? So A is equal to 2R. Now, what is the volume of that cube? Well, the volume of the cube right, is going to be A times A times A. So A cubed, right? But you know, if it's A cubed and A equals 2R, then wouldn't that be 8R cubed is the volume of that cube, of the cube, in terms of R and in terms of A. Does everyone see that? Okay, I better check my timer here, but oh my God, did I not turn it on? No, I did turn it on, so there you go. I'll just put that there. I think that I actually turned it on to like a countdown timer or something before, so I don't know if I probably should change this. Just a second. Okay, oops. Just gonna change that, and there we go. Now it'll start and it won't go off, and I'll know how much time I've got left. All right, let's go back to this then. So the volume of the cube, so this is the volume of the cube, is that. Now, how about these? Each one of these is going to be 1/4 of a half, or it's going to be 1/8 of a whole. And how many do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, right? There's one back there too. And so I've got 8 1/8ths of an atom. So the atom, the volume of the atom, right? So let's put this here. The volume of the atom, of the atoms in there, which is going to be one atom, is going to be 4/3 pi r cubed, isn't it? Isn't that the volume of a sphere? Okay. So I've got the volume of the sphere and I've got the volume of the cube. So the packing factor would be the volume of the atom, right? So packing factor equals the volume of the atom over the volume of the cube. So I have, let's just write this out, 4/3 pi r cubed. And then that's divided by, right, we could just put a parentheses there to include all of that. And then that's divided by 8r cubed, right? So let's get rid of some things here then. Well, I've got the 4, right? I can get rid of that, and I could change that into a 2. And then I've got pi and 3, and the r cubes disappear, don't they? So 2 and 3 is 6. So I have pi divided by 6, right? Now, I don't think oh, yes, I do. Yep, well, they want me to do this in a spontaneous, synchronous way, so I'm going to do it. Let's see, where is pi? I'm just 1.14159 divided by 6 equals 52.4%. 52.4% packing factor. Does everyone see that? Now, another thing that we'd really want to look at is when we look at the unit cube size of this and we look at the lattice constant, that's what A is. So A equals my lattice, take good notes, constant. And A in this case is going to be 2R, of course, but the real question is what is R? What are we looking at? What would be the radius of any of these? Actually, I just wanted to find. You know, I should know off the top of my head. I think it's 1.4 nanometers is the radius of an iron atom. Oh, wait, here you go. Yeah, I got, did I say 1.4? 0.14. And I've got a copper atom, though. It's 0.1278 nanometers, right? So if the radius of a copper atom, let's just do a little example here. The radius of a copper atom equals 0.1278 nanometers. We could talk in angstroms too, but we're engineers, so we talk in nanometers rather than angstroms. So if that's what it would be, and if I had, you know, a simple cubic structure for this, it would just be twice that, right? That's actually not what copper comes in. Copper comes in a face-centered cubic arrangement. And I'm going to talk about that next. But the lattice constant, and in this case, the lattice constant is equal to 2 times R. I'm trying to think of a metal that has a simple cubic structure. I'm trying to think of one. I know sodium chloride is a face-centered cubic structure. Anyway, well, let's go on anyway, and work on a body-centered cubic structure. This is just a simple cubic structure that we've got right here, and you can see that my packing factor, right? I'm just going to put, since I have extra space here, my packing factor for a simple cubic is going to be 52.4%. And I also want to point out that if I was looking at then a, let me just cut this off for a second. If I was looking at my lattice constant in terms of this, and I'll come back to this and talk to you about something that is simple cubic in a little while. But I'm more focused on the metallurgy and the material science of this. And really, when we're looking at metals, we're looking at things that are face-centered cubic. Good conductors are face-centered cubic in many ways. Lead also is face-centered cubic. Aluminum is face-centered cubic. So there's a lot of things that are face-centered cubic, and there are things that are body-centered cubic too. Like I said, steel or iron at room temperature is a body-centered cubic arrangement, whereas at high temperature, it turns into a face-centered cubic arrangement, and that allows it to be malleable and ductile at high temperatures in a way that it never could be at room temperatures. You've probably heard of hot-rolled and cold-rolled steel, and of course, hot-rolled is being rolled in the FCC structure, and cold-rolled is being rolled in the BCC structure. And that's what I sort of wanted to, look at with this. Okay, I'm just going to take a second. I'll be right back. Okay, I am back. Sorry about that, but I wanted to check something out for a second. What I want to do now is I want to look at, instead of looking at the simple cubic cell, and I'll let you look at the other Bravais lattice structures, but I want to point out the ones that are really important to us as engineers, and that's predominantly the face-centered cubic structure, especially to electrical engineers, because both aluminum and iron and copper, our main conductors, as well as our semiconductors, are face-centered cubic structures. So let's get back to looking at that. So that's one. That's a simple cubic structure. Let's look at the body-centered cubic structure. Okay, I'm going to look at it the same way. I'm going to do it in 2 steps here. Let's say that I've got, here's here's my, and I'll drop down some invisible lines in back because I'm not going to draw these so large. And in fact, I may even use some different colors. How about that? So this probably isn't that great a color. Let's see if I can get like a green. And so I'd have, first of all, an atom at each of the corners, just like I have in the simple cubic arrangement. But I would have one more atom. I would have one more atom in the very center. So it makes, it's going to expand the lattice structure a little bit. And you know, I want to sort of give a demonstration too of how these are set up. You know, if we were looking at the simple cubic, we would see a setup, if we were looking at it side on, that would look like this. If we were looking at billiard balls on a billiard table, right, if you wanted to think of it that way, we would see the billiard balls on top of one another, touching, each one touching the one below it and touching the one on the right and the left. I may not be able to draw it that well, but that's what I'm trying to do. So they would be sort of stacked on top of one another, right? That's the simple cubic arrangement, and that's why the packing factor of that is only 52.4%. Okay, now, when we're looking at the body-centered cubic, what we'd be looking at is we'd be looking at one row very similar to that row that you've got there, but then the second row would be in the valleys between the individual ones. And you're probably saying to yourself right now, well, okay, that will allow a greater packing factor. Look at the packing factor just as I've drawn those as compared to the packing factor that I have down there. Now, if I'm going to draw this not as a diagram like this, a simple diagram, but more like this, where we can see what's actually going on inside, we would, I'm going to draw it a little bit larger this time. Is that larger? Yes. There we go. Right? And now what you'd see is there's a huge atom inside there. And what that does is that sort of allows these are not really going all the way to the center anymore. They're not really touching each other at the center. So let me draw some of these up here. Right. And then we've got that huge atom inside too. Let's not forget that. Right, I'm just gonna sort of round that all out. I think everybody can see now. I'm not gonna draw the ones in the back, but you know, you can see that that would go down back there, and if I just dropped a thing down here. But what you've got inside here now is a giant atom itself. So there's another atom inside there. And you're probably thinking, well, you know, when we're looking at the lattice constant here, how are we going to figure that out? Because these two atoms aren't touching here, are they? That's right, they're not touching there. Where are all the atoms touching? You know, if I took a diagonal, let's take a diagonal all the way through that. So let me just draw this again. I'll just draw it down here and sort of draw a diagonal through here. Right, so let me use, I'm just going to drop this down so that you can see what's going on behind the scenes too. There's my hidden lines behind there. Now let's go from diagonal. Let's go from here all the way over to here. Right? If I were to go right through the center of that cell, that unit cell for a body-centered cubic arrangement, right? This is usually BCC. Simple cubic is SC. if I was going to go through the BCC and look at that, what am I going through? I'm actually going through a radius here, right? Then I go through 2 radii here, and then I go through another radii here, because along this line, they're all touching. So that would be 1, 2, 3, 4 radii along there. So I know that that diagonal equals 4r. So let's do that. So that diagonal equals 4r. Now, what does it equal in terms of a? Right? We know that distance is a. It's cubic, so we know all the sides are the same. So this distance here is a, this distance here is a, and this distance here is a, right? So we can use Pythagoras' theorem, Pythagorean theorem here. I've got a squared plus a squared plus a squared equals, let's call this d for diagonal, d squared, right? Does everybody see that? So what would that be? That would be a squared plus a squared plus a squared is 3a squared. So if I took the square root of 3a squared, that would give me the square root of 3 times a, right? So I know that a, for a body-centered cubic arrangement, right, is going to be equal to 4 over the square root of 3 times r. All right? So what would the volume of the cube be? Well, the volume of the cube equals a cubed, doesn't it? Well, we know what a is, so we can now write it in terms of r. So I've got a cubed, or I could say that it would be 4 over the square root of 3 times times r cubed, right? 4 times 4 is 16, times 4 is 64. So 64 divided by 3 times the square root of 3 times r cubed. Have I lost anybody there? I'm just cubing this. 4 cubed is 64. And r cubed, and then square root of 3. Well, square root of 3 times square root of 3 times square root of 3 gives me 3 times the square root of 3. I think everybody can see that. So that's the volume of the cube in terms of A and in terms of R. Now, how about the volume of the atoms? Because, you know, I say atoms instead of atom because we've got 2 atoms here, don't we? Don't we still have the 4 octets of an atom? So that gives me 1 atom. Then I've got another atom inside. So that's really 2 atoms. So that's going to be 2 times 4/3 pi r cubed. Right? Does everybody see that? Oh, I've got to move my chair over. I realized, oh my God, I'm twisting. I'm, going to screw up my back here. So what's the packing factor then? What is the packing factor? Wouldn't that be the volume of the atoms over the volume of the cube? So let's just make a long fraction there. And I've got 2 times 8, volume of the atom, so that's going to be 8 over 3 times pi r cubed. There's the volume of the atoms. I'm going to just put a parentheses around that, times, or divided by, the volume of this, which will be 64 over 3 times the square root of 3 times r cubed. Right, I should have extended that further, but you get the idea. So the 3 cancels out with the 3. The 8 cancels out with the 64, leaving 8. The r cubed cancels out with the r cubed. So I've got the square root of 3 times pi divided by 8. Right? Let me just grab my calculator for a second. Where's my good calculator? Okay, so I've got the square root of 3 times pi divided by 8 equals 0.68, or 68% packing factor, right? So you can see, as we thought, the packing factor for an arrangement like this, where each individual rows of balls are fitting like in between, and they're actually, you know, along here, they're connected, but anyway, I think you can see that that's a better packing arrangement than a simple cubic packing arrangement like we've got over here. Now, body-centered cubic structure, that would be for iron, or we could say steel, but I'm just going to say iron. And I believe that iron, now let's see, well, I wish that, you know, I'm just going to look, you know, because I love iron and steel so much. I'm just going to take a second and look up iron's radius. I think it's 0.14, but let me double check that. Oh, where'd it go? Something's going on here. I thought that, oops. Okay, now I'm back. I don't know what happened there. I was going to pause it, but boy, just a second. All right, class, I am back. And no, I was wrong. But I want to point out something to you anyway. Iron in its BCC state, the radius of iron in its BCC state is 0.124 nanometers. And that's not the same in its FCC state, which I'm going to talk about in just a second. In its FCC state, the radius of iron is 0.1263 nanometers. And I want to compare that to in the, you know, lattice constant of when we're looking here. So in the BCC lattice constant for iron, A for iron, I'm just going to put Fe down here for so that you know that in your notes it's the lattice constant if we were using an iron and not a copper. I mean, you could see copper, which is FCC. Well, I'll talk about that when I do the FCC example, but you can see that, well, you will see. Let's just do that. So A is going to be 4 divided by the square root of 3 times 0.124 for BCC room temperature iron, and that gives us a lattice constant of 0.286 nanometers. You could talk in picometers too. You could say it's 286.4 picometers if you wanted to, but I'm just going to, you know, talk in terms of nanometers. We could talk in terms of angstroms, but that's scientific. That's not engineering. So you can see that for this lattice constant right here, if I was doing this, and if iron over here, you know, was being used, the 0.124 BCC iron was being used over here, that would just be 2 times that, wouldn't it? Because the lattice constant is just 2 times R, and 2 times 0.124 would be 0.248, right? 0.248. So you can see the lattice constant here is a little bit bigger because you've got that space in between there. Now we go to the third one of what we're looking at, which is going to be the FCC, or face-centered cubic crystal lattice structure. And when we look at the face-centered cubic crystal lattice structure, I'm just going to draw a line down here. We see something that looks more like this. In each of the individual, we still have this. This is pushed even further apart, actually. And I'm going to describe the difference between each one of these. But you can see that we've got an atom there, and then we've got our quartet still here. And of course, that's expanding out. I got to draw that larger. That's expanding out even more than it used to be. And then on each one of these faces, we're going to have half of an atom, aren't we? So when we look at how many atoms are involved in here, we've got 1/2, 1/2, 1/2, 1/2, right? And 1/2 and 1/2 down on the bottom. So we've got how many faces here, right? 4, 6 faces, each with half an atom in it. And that's going to give me 3 atoms. And then how about our octets that we've got here? That's going to give me another atom. So I really have 4 atoms in here, don't I? And if we were looking at this, what we would see is we would see that if I put down that first row of atoms, and then the second row I actually push down, but I push down on them. I actually am pushing down on them further so that the row below, right, actually expands. And then this row naturally would be sort of expanded that way, and those would push down inside it. So it has even a higher packing factor than the body-centered cubic arrangement that we had over here. And that's what happens. And also when we look at this, let's not forget that the R for FCC is a little bit larger. It's 0.1263 for an iron atom. But let's look and see what we've got here. Now, if we were to look at this face, right, these are touching along the face, aren't they? Do you see that as I go along this face, there's R, there's R, there's R, there's R. So I've got R stretching across that face, and the 2 sides here, this side here, right, is A, and this side down here is A. So I've got 4R equals A squared plus A squared. So 4R equals 2A squared, right? So if I wanted to find A, I could take the square root of both sides. Well, the square root of, actually, why don't I do this? A squared, and I'm sure I won't lose anybody either way, but I'll just do it this way. So A squared equals 4 divided by 2. 4 divided by 2 is going to give me 2R. Does everyone see that? So if I wanted to find A in terms of R, wait a second, what have I got here? 4R is square root of 3A, yes. Yeah, that's right. Let me check something. I'll be right back. Okay, sorry about that. So 4R equals the square root of 2A squared. So I want the So that would be A, let's get that. A equals 4 divided by the square root of square root of 2, 4 over the square root of 2 r. Have I got that right? 4r, square root of 2. Yep, 4 divided by the square root of 2 times r. All right, so let's let me write that again. A equals 4r divided by the square root of 2. All right. So we see that, and then we want to find out what our packing factor is going to be here. We could figure out what R is. I'm going to leave that there for just a second. But to get our packing factor, we want the volume of the atoms divided by the volume of the cube. Well, the volume of the atoms, I've got 4, right, times 4/3 pi r cubed. Let's put a parentheses around that. I'll put a little equal sign there. And then we want to divide that by the volume of the cube. Well, the volume of the cube then being a cubed, right? So a cubed equals 64, right, times r cubed over 2 times the square root of 2. I might write it out that way anyway. It's probably easier anyway. Well, why don't we say 32? So 32r cubed over the square root of 2. I'll do that. So 32r cubed over the square root of 2, right? So my packing factor, and we know that equals our packing factor. So our packing factor, let's get rid of some of these. I've got 4 times 4, well, that's 16, right? So 16 and 32, that makes that equal to a 2. And doesn't that square root of 2 and the square root of 2 sort of and the 2 sort of cancel out? So that could make, anyway, we'll leave it there. We'll leave it there for a while. But let's write these things out. So I've got the square root of 2 times pi times r cubed divided by 3 times 2. Oh wait, that should be that should have been a 2 there, right? Didn't I? Wasn't I? Oh, I put a 2 down there. Okay, so that 2. Oh, better put a line through there so I know which is which. So that 2, of course, is down there too. So let's see, square, 3, yep, okay. So 2 times 3 gives me 6, 6r cubed, and the r cubes cancel out. So I get the square root of 2 times pi divided by 6, and that should equal 74.5, but I'm gonna punch that in and make exactly sure of that. So the square root of 2 times pi divided by 6 gives me 74.04. Okay. 74.04%. And you can see that the packing factor for that, thank God that worked out, is bigger than that. Also, what is A for this, right? Let's do that. A for the FCC, right, is going to be more, isn't it? Because we know that A is 4r over the square root of 2, and if we use the 0.1263, so 0.1263 times 4 divided by the square root of 2 equals 0.3572, right? So 0.3572 nanometers for the thing for FCC. And of course, this is for iron, right, for iron in its FCC state. And if we wanted to look at A for the BCC iron, that would be equal to, we already have it down here, 0.2864 nanometers. So don't get the lattice constant, like the lattice constants all have to be the same or something like that. That is not true. That's for iron, and that's for the BCC iron. Okay, hope you had a good time with the lecture today. I have no idea how long it is, but I'm going to do it, and that's a good introduction to lattice constant. When I am teaching this, I'll be breaking in all the time to, you know, make comments and everything like that, but I think this gives a good starting point in making sure that we get through the amount of material that we have to. Okay.